So doing Monte Carlo tree search in the Ghost game turns out works okay. To get a decent measure of whether an action is good or not takes 100 simulated playthroughs of the game. To be consistent in whether you, to be consistent in your good action choice, you need maybe 1,000-ish. And in practice, that's not too bad. Rolling out simulations in the Ghost game is cheap. You can do it in parallel. If you have parallel processes, just each one of them does a separate simulation, and then you just combine all the results in the end. And it just kind of, it works out okay. One of the key issues is that I don't have a very good definition of what okay is, and I'll get to this later. So eyeballing it, it seems like the sidekick does things which are good. And then finally, working out, okay, so there are some subtleties which I'll just briefly touch on. Monte Carlo tree search has previously been used in games like Go and checkers and other things which have like a defined terminal state. In chess, it's when you checkmate, somebody's checkmated, or when there's a stalemate. In Go, it's when like all the positions on the board are filled up, and you can't repeat board states because there's code rules which stop you from doing that. So in those two games, there's no sense in which a game could go on forever. But in the Ghost game, there is a sense in which the game could just go on forever. So just say that you choose to do nothing, and then, so the human chooses to do nothing, and then the sidekick chooses to do nothing, and then all the ghosts choose to do nothing. And then they do it again, and again, and again, and again, and again. The only way that the game ends, you'll remember, is by both the human and the sidekick standing on the ghost the human is going for. So it's possible to just never choose actions which result in that state. You can have an infinitely long sequence of states, which doesn't include a goal state. So we need to use tricks in our actual implementation to make sure that that kind of thing doesn't cause our program to run forever. And the other shortcoming of this technique is that we still don't have any model of human expectations of what the sidekick is thinking, but I have some ideas as to how to make this work. I'm going to be even briefer about this other version which I've been working on because I'm not very excited by it. It's called probabilistic A-star. So there is this classic search algorithm in AI called A-star. It's used for finding the shortest path through these things which are called graphs. For people who haven't seen a graph before, this is a graph. It's these balls with sticks connecting them. Sticks have a cost on them. And the idea with A-star is to try and work out which sequence of sticks to take from your source, so in this case up here, to your goal, which minimizes the costs which are written on these sticks. And in A-star, you do this search by taking advantage of something which is called a admissible heuristic, or just a heuristic, which gives you an estimate of, from each of these balls, what the costs on the sticks remaining to get to the destination are. And this lets you avoid exploring a large amount of the graph. So you can target your search to finding your destination efficiently, right? And the idea here, right, is that all of these balls are going to be all of the states of the world that could possibly happen. All of the sticks are going to be the actions that we can take. And when we take an action, it's going to take us from one ball to another. And the way we're going to set things up is that each of the sticks, so each of the actions, will have a cost associated with it, with the probability of the state that we are reaching, the inverse of the probability of the state which we are trying to get to as the cost which is associated with it. So what this means, right, is that we can choose to go from a state that we are in to any of the neighboring states that we can reach by an action. But it costs us an amount to go that far, which is proportional to how unlikely it is that we will actually end up in that state, given that we chose the action that we did. So if we choose a fabulously unlikely state to go to, then it costs a lot. If we choose a very likely state to go to, then it will just be quite cheap. And where the probabilities and all of this stuff comes from is like the only thing that we can't control as players, or as a sidekick, which is the actions which the ghosts take. So essentially what we're saying with when we do this probabilistic A-star thing is we can plan a trajectory through these state spaces, trying to reach the goal where we're both standing on top of the same ghost, and it's the ghost that the human is aiming for. So we can plan a trajectory, and we're trying to find the cheapest trajectory, where the cost that we pay for taking each step is like dependent upon how unlikely our action will be successful is. Okay. So again, this kind of approach does work, but it performs poorly, unfortunately. And the reason for that at the moment is because I noted for A-star you need this heuristic which gives you an estimate of how far you have to go. It turns out that in the case of the Ghost game, and also in the case of Dearth, it's hard to find a really tight heuristic which will tell you exactly what the distance is, and always underestimates the distance, but like is not a dramatic underestimate. So, also, although I haven't seen it, there is definitely the potential for the planning system doing strange wishful thinking things. Like it could, for instance, say, yeah, I'm willing to risk my life in order to, and pay a huge cost in order to take a really good step in the world, despite the fact that it's incredibly unlikely that I could ever do that and survive in the real world. But potentially the way that I've set things up, that could happen, and I could come up with really horrible really horrible examples which would like be totally horrific and demonstrate this kind of thing. But in practice, it kind of seems to work okay, and you get a sidekick which can do its thing. All right, so this is the final slide. I have these two prototypes, which are complete in that we can do online planning in a game which is like Dearth. And by online planning, I mean real-time planning. So it'll respond to humans' actions in real time, do the planning, and then update the state of the world by taking the agent's action. Rather than having to pre-compute a policy and then loading it into memory later. And they achieve this by avoiding having to store full policies, which is what I was talking about before. So we don't have to consider every single state that we might reach in the world. Instead, we only have to consider a sort of subset which we're likely to reach. The Monte Carlo tree search version works pretty well. It's pretty fast. The A-star version is not particularly fast. It's only kind of pseudo real time. And if I had a better heuristic which could guide search in these state spaces, then both of them could be better off. And so the next possible steps that I could take, there are two directions, right? One of them is this model more interesting things, and another one is this scale up to interesting problems kind of direction. In the model more interesting things direction, we have things which are along the lines of, so just say that I wanted to have my model be more responsive to what it thinks that a human is thinking about it. Might want to do that. What if I wanted my agent to be able to communicate with humans? Would that change things? It's an interesting thing to talk about, to think about. And then on the also you could do things like attempting to deal with the problem of what do we do about when we can't see round corners. I mean, we know that the optimal solution for this kind of deck POM-DP is undecidable, but I mean, if we use these kinds of approximate methods, which I've been presenting here, then it might not be so bad, and maybe we can come up with something clever to do that. Or we could try and scale up these solutions which I already have. So in the case of Monte Carlo tree search, what I might want to do is I might want to write code which will parallelize it and make it really fast. So I could do it with large state spaces and with more agents and all this kind of thing. But it's kind of unclear like which of these is the best direction. And then the other thing which I need to do kind of a bit more urgently is work out what the right thing to measure about these two approaches is. Like, so eyeballing them and playing with them, like both of these systems that I've briefly described can deal with Dearth, and they can deal with the Ghost game, and they can play a game as a sidekick, right? But sometimes they do things which are a little bit weird. Like, which one of them is better than the other? In what sense do I really mean better? And like, how do you exactly measure that? Would you get somebody to sit down, play with both of the agents, and then fill out a questionnaire and saying which of these two agents do you think is more responsive to your goals, or what's the right metric for measuring these things, and how do you go about doing it? It's not entirely clear. So yeah, that's where I'm at the moment with my research, and that was a whirlwind tour of what I've done this semester. All right, thank you.
Questions, right?
Yep.
I was just wondering, in terms of, you said these are the kind of things that, you talked about this in terms of like being beneficial for game AI and game makers, and I'm wondering, do you see this as primarily something that is a time saver, or something that's going to actually change what kinds of AI we see in games, or both?
Okay, so there are definitely those two things. So time saver in terms of, if you have a general system which allows you to do planning, then you run the planner on your new game, and then it just comes up with the AI behaviors for you. So that's the sense in which it's a time saver, right? Nobody has to sit. So the coding that you would have to do is to transform, or to generate a representation of the game state so that the agent can use its planner on it, right? So that the sidekick. So you'd have to specify what is the state of the game, and how the actions take you from state to state and all this kind of thing. And then once you've done that, you just kind of throw it into your black box, and out pops the best way for your agent to behave. So that's one thing, right? So there's time saver in terms of development. Then there's also what if I were creating a game and I just didn't really have any idea what a good strategy was? I mean, like, you can imagine that there might be incredibly complex interactions between elements of your game that you found it hard just to kind of think about. And like, this is particularly apparent in strategy games which have like complex underlying systems and what have you. The idea then would be that you could use this to create an AI which you would not be able to hand code. So it may be just beyond your capacity to be able to reason about what an actual good thing to do for an AI would be. But if you had an automatic planning system, you could just throw it into the black box and it would spit out what the answer was. And you might not be able to understand why it's the right thing to do, but your automatic planning would.
So if it achieves sentience, then that would be even cooler.
That would be totally sweet.
So would you also call this kind of like AI middleware, perhaps?
Yeah. So the idea is that this would be AI middleware. That's
tools, at least.
Yeah.
It seems to me when you were talking about how to measure quality, and I was thinking this before you even brought that up, that, you know, I think everybody has a different opinion about what intelligence is, right? Or what their sidekick should be doing. Mm-hmm. I think if your sidekick's too smart, it's not going to be fun for the player at all, you know. Seeing the, I could imagine playing Dearth, for example, and I want to go over here, and then I see him doing something that's counterintuitive to me. And I'm wondering to myself, why is he doing that? Well, if he's the AI, he must know I should probably go in that direction. Or, you know, so like, what sort of interaction?
So this is interesting and weird, and like actually pops up quite a lot when you're doing this kind of development. So I know when I was working with the computational and cognitive science people across the road in brain and cognitive sciences, we were working on, again, kind of these little mini games which have AIs that use this kind of Markov decision process set up and value iteration solutions to go through and solve them. And sometimes the AIs would do things which seemed counterintuitive, but then, and we thought that there were bugs.
Sure.
And then we'd look into it and find out that no, in fact, like it's just not how humans intuitively think about solving these kinds of problems. And so it looks like the AI is doing something weird, but isn't in fact totally rational and the best thing to do.
I mean, I picture
and it's hard to, yeah, I mean, and it's hard to know what to do about that, right?
Yeah.
So if you do develop a system which plays optimally, but playing optimally looks strange, like it looks like a non-human way to play, then that's a legitimate concern. Like it may be incomprehensible for a human what their sidekick is.
Right. I mean, even though the AI might be more intelligent, you know, having players test it and, you know, which one is perceived to be more intelligent, which one's perceived to be more helpful, that sort of questionnaire that you're getting at. Because I mean, I would think that, to me, an AI that, you know, say I just happen to take right-hand turns more often than left-hand turns, and to have the AI sort of learn my particular play style more and sort of have it feel more natural. Does it take into account the movements of the player? Does it sort of track and have a memory for these things?
So this adds this extra element to the modeling that the AI has to do. So what that would be is you would have extra unobservable parts of yourself other than just your goal. You would also have like your left turn or right turn propensity, which needs to be included in the model that the AI reasoning system is reasoning about. So I mean, you could include these things, but then, I mean,
I was also wondering, does it have to just be one model? Can it be that you use, you know, the sort of the reward sort of system with the grid, and then you also use the sort of improviso sort of style where you're charting and graphing other people's play, and then you're using the sort of evolution style where you're running simulations under the hood, and then you.
So interestingly,
I know processing becomes time, but then you sort of get the results of all those things and.
So this business here,
and vote.
That's actually pretty. That technique is kind of used sometimes. You might this not so much in MDP, but there are definitely techniques where you try to analyze the behavior, and one analysis, and another analysis you might run it twice and get you very different results. But you run it 10 times and have them all vote.
Because it seems to me that's a sort of intelligence, right?
There are ways of aggregating different planning systems and what have you. So the simple way to think about it here is like, this thing here is where this slots in. So if we go back to Monte Carlo tree search, this is the most obvious place. We might have prior information about like what a good move to make is in any given state, because we've seen humans play, right? And so if we assume that humans are going to do something which is, you know, all things considered pretty good, then we should, like, by default, try and mimic humans, right? So when it comes to doing this, that is, we're in a state that we personally, as a sidekick, have never experienced before, but we've seen a human do something when they were in this state before. Then we might, rather than just picking some action at random, pick the thing which the human does most frequently. And that's where these kinds of approaches, like the empirical data is provided by humans, plus like our own simulated experiences as the sidekick, might be brought together. Yeah.
I mean, I could really, just going from beginning to end, playing a game that has a sidekick, I would really feel connected to that particular sidekick if it was responding and sort of, if we start off the game and we were fumbling, you know, and it sort of learned from me and I learned from what it was doing, and you know, there was a good mix of things, because it seems to me that I would never call something very intelligent if it always approached things the same way, you know, and if you can start to sort of see that.
So trying to work out what the human doesn't know about the world is a really interesting direction to go with this. So that would be developing a more rich model of the human and the human's like cognitive shortcomings or what have you. The way things are set up for Dearth, for instance, assumes that the human will just play its half of an optimal plan, which includes the sidekick and the human, right? But humans might not play optimally. and it may look weird to a human that their sidekicks like expected him to play optimally. Or humans may not know things about the world, which the sidekick does, which may make these sidekicks' actions look strange to the human. And in that case, you might want to build into your reasoning system a way of working out what it is that the human doesn't know, and then performing actions which compensate for the human's knowledge. So if you add communication actions, then you might just tell the human that like there's a secret door over here, and that kind of thing.